And we are back. Happy Wednesday, March 17th. Chapter 25, still moving along. And this is our last chapter before test 3 here. So next week, next Tuesday and Wednesday coming up quite quick. Um, and we don't have class on Friday, but we'll of course have class next Monday where we'll wrap things up and review. If you want to start looking at the sample test, I know some people already have yesterday in recitation, talking to some people there. Quiz 7 is posted. If people seen that, that's on Learning Suite already. I was helping a couple people with that. So you have some time with that still to go. And yeah, homework 10 is for this chapter 25, and we'll give you till next Monday. So yeah, quite a few announcements there. Hopefully we can keep things straight. We will have, of course, test 4, the final midterm, after we do the biomolecules at the end there. Questions on any of this stuff? I think that's okay. Yeah, check out Learning Suite for the sample test, and keep up to date on working the chapter problems. That's the best thing to catch up with and practice the material there. Even though we don't have class on Friday, we should be able to help you out with everything. And of course, through the quiz, you have recitation on Thursday, so you can still get some help there in office hours, of course. Questions on anything? All right, Gannon, let's do the overhead here first, I think. Just to remind you, we did go through the introduction of the amines before, of course. I just wanted to point out the reactions again here. We will talk about alkylation of amines in general, but that's not a very efficient process. It'll often give over-alkylation. If we want to give just monoalkylation and make a primary amine in high yield, we often use what's called the Gabriel synthesis, and that's with the phthalimide anion. To make secondary and tertiary amines in high selectivity, we start with aldehydes or ketones in amines and do what's called a reductive amination. We'll use a new reducing agent, sodium cyanoborohydride, which is analogous, of course, to sodium borohydride. It'll supply a hydride to the iminium ion in both cases and give us amines with high selectivity there. We'll talk about basicity of amines. We'll look at it from the conjugate acid point of view. Remember we said protonated amines, ammonium ions, have pKs of about 9. Those are very weak acids, okay? And they can give up a proton and go to the conjugate base, which is the free base here, we would say. And so we'll look at the stability of that free base to talk about basicity, how strong of a base that is. And that has to do with how available the lone pair of electrons are here. They're not shown, but that's why it's a base, right? Those lone pairs can grab a proton and form the ammonium thing. Now we'll compare this to the heterocyclic amines. Here's protonated pyridine or pyridinium cation. That has a pK of 5, okay? Which means what? It's a stronger base. It has a lower pKa, which means what? Or it's a stronger acid, sorry, which means the base is actually weaker. And we'll see why. We'll talk about the factors to see there. But focus on the conjugate base there and how stable that is. That's kind of the key thing. Yeah, and then Hoffman elimination, we are eliminating. There you go, omitting section 12 there. We will do nitrosation and look at the Aryl diazonium cations and how they react to form different things. No mechanism there. We won't hold you to the mechanism. You just have to know the reactivity. So it's second level of understanding, reactivity. And we'll do some synthesis there and show you why those are important. We will do electrophilic aromatic substitution on the aryl diazoniums to make the diaryl compounds. Those are important for various applications, including drugs and dyes, colored materials. So good, let's go to the sideboard here and look at alkylation. And this is a reaction you've already seen before, right? So this is that process where we just take an amine and, add in the pair of electrons. And we've talked about this before. Even though it's neutral, that is a good nucleophile, okay? It's 2.8 on the Pauling scale, so it's not as electronegative as oxygen. So those lone pairs are not held as tight okay? So it can react with primary and secondary like that SN2. And that initially forms what? A ethyl ammonium cation and the bromide counter anion salt form. But you see, if we've got ammonia here, excess of this, it can deprotonate that. What? And then we can have the free base again. And then that free base can do what? More alkylation. And that would be what? Diethylamine. Okay. And I'm leaving out the step where we deprotonate that. So there is another step here, I guess, to deprotonate that. And then you see that can add a third ethyl group. Okay. So you have the tertiary amine, primary, secondary, tertiary. And then you still have a lone pair here after you deprotonate. So this is that extra deprotonation step again. And then if you have excess of the alkyl, you can end up with that actually as your major product. Okay. And even if you try to control this, you'll often get di and even tetra here, even if you try to control it. The way to get around this is to use excess of the ammonia, you see? And so you'll react this, okay, in the presence of more ammonia, which will deprotonate that. And that'll stop there as long as that uses up the equivalent of the primary amine. But that's using a lot of ammonia. That smells bad. And even if you do control it, you might still get some over-alkylation. So this is okay. We'll say, yeah, you can do that on a quiz or a test. But we're going to show you the more efficient approaches here, okay? And the first one is called the Gabriel synthesis. And it uses this crazy looking benzene with an imide right here. We've talked about imides before, succinimide imide. This is called phthalimide. I'm not going to write it out. It's on the overhead there. But this is a nice, stable, solid material. Doesn't smell bad like ammonia. Okay. You can easily deprotonate it irreversibly with a cheap base, hydroxide. And why can we do that? Well, normally, if we didn't have these two carbonyls there, a regular amine would have a super high pKa, right? But with the two carbonyls there, we can deprotonate that and get the phthalimide anion. Okay. So the nitrogen now has two lone pairs and it's negatively charged. Okay. And we have a byproduct of water. But that's a great, well-behaved nucleophile now. Number one, it's charged. Its resonance delocalized by the two carbonyls. And now we can use this at 1-to-1 stoichiometry with an alkyl halide. Or a secondary halide will work as well. Not tertiary, okay? So we're kind of limited here to primary or secondary. And you can see here, right, another SN2 reaction, just like before up there. But now when we get the product here, the alkylated phthalimide on nitrogen, it just sits there. This lone pair now, you see, we didn't have a hydrogen on there. And right now, this lone pair, will it over-alkylate like before with a regular amine? No, this lone pair is delocalized now toward both carbonyls, so it's not nucleophilic. Okay, it'll just sit like that. You can get a very good yield for the monoalkylation. In this case, whoa, how many do we? Oh, I meant butyl there. Okay, for the butylamine, and then to liberate now our product that we want, we treat it with this material here, and that's called hydrazine. We've seen hydrazine before in the Clemmensen reduction that we saw with aromatic ketones. Hydrazine will acylate here and liberate the primary amine. There's a number of steps here. I'm not going to do it. You could go through that mechanism. It's kind of a minor point. You wind up with this. The phthalimide ends up as the hydrazine analog. And what's liberated here is what? What comes out is the primary amine in very high yield. So if our alkyl group is something we've invested a lot of time to make, if it's an expensive material, whatever, we wouldn't want to alkylate it with ammonia. We'd get a lot of over-alkylation and a lot of byproducts we may not want. If we want this primary amine and high selectivity, high yield, we'd use the Gabriel synthesis. No over-alkylation, okay? We do this at 1-to-1 stoichiometry with high efficiency. And then that lone pair here is dead because of resonance, not nucleophilic anymore. So let's say, you know, not a nucleophile. Unlike this, where you could easily deprotonate, right, the ammonium cation and get over alkylation, here it stops. Okay. Questions on the Gabriel synthesis? I think that one's pretty straightforward. This other approach here to make secondary and tertiary amines is also pretty straightforward, I think. This is called reductive amination. And how do we do reductive amination? Well, we already know how to react a ketone or an aldehyde with a primary or secondary amine. So here's a primary amine. All right, if we add a little bit of acetic acid, we can get what to go better? So this goes back to the previous section, right? We talked about this. And that's an intermediate on that after we lose water, right? So we can think about this even under neutral conditions. But if we're under acidic conditions, we would have this protonated, right? And that's our pathway to what? To form the neutral imine, right? With a primary amine. Now, at this point, we add a compound called sodium cyanoborohydride. Now, what is that? Well, we saw sodium borohydride before, NaBH4, right? So what is this with a cyanide on there? Well, it's the same thing. Borate is negatively charged because it has 4 things on it, but it has this cyanide on it. Let's see, a cyanide has a triple bond. It's bonded to the boron. So maybe we could draw that out. You know, it's got the 3 hydrides and the cyanide on there. What does this cyanide do to the reactivity of the hydrides coming off? Well, a cyano group, because it's conjugated over here to the more electron nitrogen, that's what? Actually an electron withdrawing group, okay? And by having that property, sodium cyanoborohydride will not reduce the starting ketone or aldehyde. So remember, we did sodium borohydride, BH4, without the withdrawing group. That would easily reduce what? Aldehydes and ketones to alcohols. We don't want that. You can actually add all these things together here and do the whole reaction here. And why this is in this chapter is we go to this. We go to the secondary amine, okay? We have the alkyl group on here, which came from the aldehyde of the ketone. And we have the original alkyl group from this primary amine starting here, okay? So this is different now. This is not our imine or our enamine we saw before because we have the hydride reducing agent. Well, how does it work? Well, hydride just adds here, okay? There it is. But the cyanide is on there to eliminate the ability to just reduce the ketone or aldehyde starting material. The aminium ion here is more electrophilic. That's a better electrophile in this case. Why? Because it's plus charge at that point, right? So that will accept this hydride off the sodium cyanoborohydride, but the ketone or aldehyde will not. Okay. Questions on that? Let's show another example here where we do it with a secondary amine. So how about this one? So same thing here. In fact, we'll just put them all together. Sodium cyanoborohydride and the secondary amine now. We can have a little bit of acetic acid in there. Doesn't matter, it'll go with the neutral stuff also. Same thing here. This is a secondary amine now. And before we went to the enamine, right? But the intermediate for the enamine, remember, is also this aminium ion, right? And remember, it did the enamine because we didn't have any hydrogens now on the nitrogen. We could only remove a hydrogen here. But instead of removing the hydrogen now, what do? Sodium cyanoborohydride does its thing. And look, we efficiently go from the ketone or the aldehyde with a secondary amine now to what? To a tertiary amine with high yield, high selectivity, whatever. And it's that hydrogen right there, tertiary amine, that we can form in high yield, okay? So this becomes a very efficient approach synthetically. Here we can think about any of these bonds here being made synthetically from the aldehyde of the ketone. In fact, let me show you another way to make this intermediate here. You can actually take this amine, cyclohexylamine, and use 2 equivalents of acetaldehyde, which is cheap, and what? Excess of your sodium cyanoborohydride. And look at that. I think you can go through it. Form the aminium ion here, reduce it, okay, form the aminium ion again, because you'll initially form a secondary amine from the primary, and then you'll form the tertiary amine here, the same product with that second equivalent of acetaldehyde. And so, you know, these 2 carbons here came from the aldehyde in that case. Initially, this carbon here came from the ketone when we made it from cyclohexanone. But this allows for some versatility for forming amines, okay, this reductive amination approach, okay? But it all hinges on this same thing, this aminium ion. Let's draw that out, because that's kind of a key thing. That aminium ion right there is the key intermediate in both cases. But you see the versatility. We can make things a couple different ways, okay? Good. Questions on that? Yeah, there's a lot of variations of that. Pretty much any aldehyde or ketone or any amine, especially for making secondary and tertiary amines. This is really the workhorse synthetically, okay? For primary amine, the Gabriel synthesis is really the best way to go. Okay, questions on any? All right. Let's get into basicity issues here. And this is an important topic, I think. It ties a lot of things together, and moving into amino acids and the biomolecules, knowing what the ionization state is of different molecules. Amines, because they do have the lone pair, are basic enough, depending on the pH, to be protonated or deprotonated, right? So we've got this ability to be neutral or to be charged. And that changes the properties quite a bit. And you'll see in biochemistry, there's a lot of biochemical pathways where it really depends on whether an intermediate is protonated or not, okay? And the key intermediates for a lot of reactions with catalysts is the catalyst can protonate something and allow for a reaction to go, or deprotonate things at the end. So you'll see that this proton on, proton off thing can be quite important. Let's look at this guy, which is an ammonium cation. And remind ourselves what the pKa is. You know, I've been telling you since 351 that, you know, ammonium cations are what, about 9? Now I'll give you some specific numbers. This one is 10.8, okay? And that's, you know, still a weak acid. It can be deprotonated, and it's in that pH range of 0 to 14. So if you're up above this 10.8, if you're at 12 or 13, whatever, that could be deprotonated. And let's, you know, think about that. You know, that would be the free base, and we've got the protonated form there. How about this, though? Let's compare that to this and have an aromatic group on there. So that's anilonium cation, if you remember that term there. And aniline is the free base, right? And, you know, what's the pKa of that? Now the structure is a little bit different, right? We've got the aromatic benzene ring right next door. And what effect does that have? These are both primary amines, right? Just one group on them. What's the pKa here? Well, it's 4.6. Look at that. It's a lot more acidic. Remember, the lower the number means higher acidity. So this is your stronger acid, okay? And what does that mean here? Well, stronger means this is your weaker base, okay? So let's see. Why is this a weaker base than this? Well, this has an alkyl group on it that's sp2 hybridized, right? Or sorry, sp3 and ethyl. And that ethyl can actually be electron releasing It's an electron-rich group. Of course, this bond here is polarized this way already toward the more electronegative nitrogen. And this more electron-rich alkyl group can actually increase the electron density there of that lone pair. But this lone pair here, now let's talk about that one. This is next door to an sp2 hybridized carbon, right? So, why is this a weaker base? You could say, well, if this guy is conjugated to the benzene, and let's draw it so it is conjugated here, right? In fact, let's put the lone pair in an sp2 hybridized nitrogen, right? And so this lone pair is actually in a p orbital, okay? And why are we doing that? Well, it's so we can have conjugation overlap this way. Well, what does that do to the basicity here? Well, it makes it a weaker base, okay? So if it does protonate, right, it becomes what? A stronger acid. And you could look at the other way. Why does this bond want to break more easily? Well, it's because the lone pair that's liberated can be resonance stabilized now, okay? And that's pretty dramatic, 5 pK units actually. So aniline is a weaker base because its conjugate acid, you see, is stronger. And you can argue for either approach, but really the main thing is here, this lone pair now is really in a p atomic orbital, okay? And that's able to conjugate and by resonance make that less available for bonding there. So, the nitrogen being sp2 hybridized versus this nitrogen here, you could say, well, that's just got the 4 groups on it. That nitrogen would also be sp3 hybridized, okay? So that's another way to look at it. But questions on that? Let's do a couple more in this comparison here. And what I remember is all of these we're going to look at now, the aromatic amines. We'll do pyridine, also pyridinium. They're also around 5. Okay. So the amines are around 9 or 10, the alkyl ones, and then the aromatic ones are around 5. So if you are trying to memorize it, but make your understanding based on the structure of it, hybridization being the key thing here. Let's look at pyridine and piperidine. And we'll throw in pyrrole also. And these are some other heterocycles you need to know their names. So here's pyridine, and we're going to protonate it, and we're going to compare with the free base of pyridine. And let's compare with piperidine. So yeah, let's get up. Oh, yeah, I want the acid on this side. Okay, this is from pyridine, right? Pyridinium, sorry for that one. And this is pyridine. Yeah, piperidine. Pip, not pyridine. Okay, whatever. And what do we have over here? This is now a secondary amine. Okay. And the protonated form of pyridine here, pKa, is 5.3. So it's close to aniline, anilonium, at 5.3. And again, what do we have here? We have a sp2 hybridized nitrogen. These lone pairs have more S character. They're held closer, okay? They're not actually in the aromatic resonance, okay? They're perpendicular to the plane there. But then we got this one. Let's see. That's a regular secondary amine. So is this going to be higher or lower than this 5.3? Let's see. This is sp3 hybridized. So less S character. These are held further out. Okay. Which means what? Is that going to be a stronger base than pyridine or a weaker base? What do you think? Anybody help us out here? Stronger, yeah. And that's because it's sp3 hybridized now. And these 2 alkyl groups, okay, that are sp3 hybridized, are actually donating, which increases the density here also. So this turns out to be a weaker acid, okay, because the base is actually stronger base. And what is the pK here? Well, it's 11.1. Okay. So what do we say here? This is a much weaker acid now because this is a stronger base compared to pyridine, which is 5.3. Okay. What about this one? How about uh, Perol? Now this is the aromatic one. We've got the lone pair there on the sp2 hybridized nitrogen. Part of the aromatic grouping, right? The aromatic hextet. So this lone pair is very different than this. Remember, we talked about those two types of lone pairs. This is a pyridine lone pair, okay, which is on the side of the aromatic ring. This is a Perol type lone pair, which is part of the aromatic grouping. And you need to count up electrons, right? Here you have the 6 electrons by Huckel's rule inside the ring. Here you have just the 4 shown, but you need to show that lone pair. You know, draw that. Sometimes we won't show it, but you need to think about that. Can it get to the aromatic grouping? Yes, it can if you count that lone pair. And so how available is that lone pair then to be a base? And what would pyrrolidinium look like? Well, it look like that. How good of a base is Perol? How available is that pair of electrons? Weaker base or stronger base? What would you say? Weaker, a lot weaker. How available is this? And again, the stability of that conjugate base. You'd say that's the conjugate base of the acid, right? Which means what? The pKa of Perol is known. It's 0.4. So you see it's a strong acid, you'd say now. Why? Because this bond's very weak. It wants to go back to being aromatic. That's worth 30 kcals per mole, right? In fact, when you protonate with a strong acid, it has to be a very strong acid. It has to be like neat sulfuric acid to get Perol to protonate. Why? Because it's such a weak base. And where does it protonate? Not on nitrogen, actually. It protonates here. It protonates on the side. And you can kind of see why. You'll have this, which is what? Still resonance stabilized. And it kind of looks like a vinyl iminium ion, you'd say. You lost aromaticity, but it protonates over here to give this resonance stabilizing. Here you don't have any resonance with the positively charged nitrogen, you see. Here you do. Here you have an iminium ion type thing. Okay, so that's actually the true conjugate acid of this base. Okay, but again, that's a super strong uh, acid because by giving up its proton, it goes to the aromatic one there. Okay. So a couple things to compare. You know, the alkylamines are stronger bases. Their conjugate acids are weaker. Okay, higher number. Pyridine and aniline are about 5. They're about the same thing, and that's because of this sp2 hybridization thing and the resonance thing. Okay, so I think that's enough we need to say on that. And know these names. Make sure you know pyridine, piperidine, maybe. Certainly Perol, imidazole. In fact, let's do a little exercise here with a little more complicated one that has a number of bases in it. And this is a good introduction to biomolecules, I think. This is histamine from histidine. It's one of those neurotransmitters we had on the board the other day. And what we got, lone pairs all over the place. We got 3 amines here. Let's kind of go here pKa wise and see what we're gonna start out with. And we'll put the pKa's um, of the conjugate acids here. So again, that's of the acid. Okay, that one's 11. Okay, that alkylamine. And what about this one here? Well, that's a what? A pyridine type lone pair. So that pKa here is about 5. Okay. And then what about this one here? Well, that's about 0. I'm kind of giving you the, and that's what a Perol type lone pair, right? Because that's part of the aromatic grouping. So let's go over here and see structure-wise. Let's start over here at, I don't know, 14, and maybe think about it, pH 13, okay? So that's 0.1 molar hydroxide, right? There we'll actually have the completely neutral form, okay? But look, as we cross over here, and here's the pKa, our first pKa is 11. So let's go over here to this point. So we're on the acidic side of this pKa. So what will we have? Well, we'll have that protonated, okay? So the primary amine will now be protonated. The other two aren't protonated yet, right? Okay. The strongest base here is the one with the highest pKa of the conjugate acid. So it'll be this. So the overall charge here will be +1. Okay. Here the overall charge was 0. What's our next pKa? Well, here's neutral water, 7. And if we get here to 5, and we're in this domain now, now what are we going to have? Well, we'll have that one protonated. Okay. See, we're on the acidic side now of that pKa. So I'll have that. And what? This guy over here is still protonated, right? So what's our overall charge at that point? Down at 3 or 4. Our overall charge will be +2. Okay. Now, how do we protonate this one? Well, we gotta go below 0. Can you go below 0 on the pH scale? What is the limit there? Well, it's limited by how many molecules of water or whatever reagent you're talking about you can have per given volume. I think the limit for water is -2.5 pH. Have you ever heard of that? Super acidic solution. Very dangerous solutions. But you need to go down here lower than 0 to what? Get this to protonate here. Well, actually, it'll protonate either here or here. But there, the overall charge, and I'm not going to draw out the structures, but you can see if you're actually lower than 0, you'd get a tri cation here. Uh, but that exercise kind of, and you could go in the opposite direction, right? If you started here with the trication and go over to here, then you get that one deprotonated, okay? And then if you move over to here, keep getting more basic, then which one do you remove next? You move that one next, okay? And then you keep the one that's the most basic until you get above its pKa of 11. So keep that in mind, especially when we think about these biomolecules. And this is one, this is that neurotransmitter histidine, okay? Histamine, sorry. Histidine is the amino acid. We'll see that coming up in the next section. Anyway, questions on that? Just conceptually. We could use the Henderson-Hasselbalch equation and at different pHs, but I don't do that on my quizzes or tests. But later on in biochem, okay, they will do things like that where you've got to quantify, you know, the ionization states of different things. But I think conceptually that's fine right now. Questions on any of that? All right. Let's look at aniline here again. We were just mentioning aniline. Let's get it back up here. And aniline, when we did electrophilic aromatic substitution, we had some issues with aniline. We were able to do some of the electrophilic aromatic substitutions on aniline, but do you remember the problems we had with aniline? What was the main issue here with aniline? And aniline, you know, is aminobenzene. It's that parent name. You already know, we've covered. Aniline, could we do Friedel-Crafts with aniline? What happened with Friedel-Crafts? Remember, that's with the aluminum Lewis acid, trying to alkylate or acylate. What did aniline do? The lone pair was basic enough to interact with the strong Lewis acid, the aluminum, and shut down Friedel-Crafts. We couldn't do Friedel-Crafts. What about nitration under acidic conditions? Nitric acid, sulfuric acid, those pKs are very low, so it could easily protonate. The anilonium now, you know, is what, around 5? So that'd be certainly enough to protonate aniline and again, give a positively charged anilonium cation right there on the ring. And so those wouldn't react either. So, in fact, if it did react at all, it would give meta products, okay, because of the cation. So there are some issues here. If we form, though, the amide on aniline, say we've got an acid amide now, we put on the group there, and we can do that with acetic anhydride and pyridine, okay? And we made amides before, and amides now, the lone pair is tied up in resonance this way and this way, and you see that attenuates its basicity. So it doesn't interact with Lewis acids anymore. Now we can do Friedel-Crafts, okay? And that was fine, okay? So anilines, depending on what you've got on the nitrogen here, an amide is well behaved, and then we know how to take that amide off. We can hydrolyze that amide off, right? But the aniline itself, the neutral amine here, has some issues because of its basicity, okay? What's another reaction we can do here with aniline? Well, we can react it with nitrous acid, HONO. Sometimes called the oh no reagent, because this late chapter in the semester, all of a sudden you got to learn another reaction. And the response of some students is, oh no, not another reaction, Dr. Andrews. Well, yeah, this is one more reaction. So this is the new thing, okay? You can make nitrous acid. It's analogous to nitric acid, which we did before. Remember, nitric acids is what we did to do nitrations, right? And that was this NO2 cation, okay, the nitronium cation here. Here we're going to form a different type of oxidized nitrogen cation. This is a nitrosyl, the nitrosonium cation. It's different. It's one less oxygen. And it'll react differently here. The NO2 cation, remember, we did electrophilic aromatic substitution with it. That was different. That was nitric acid, HNO3, and sulfuric acid. Now it's nitroso acid, okay, or nitrous acid, okay, which is the lower oxidation state. And this will form this guy, the nitrosyl cation, and this will form a different compound. It'll form this, okay, which is a nitronium or a diazonium. Let me get that up there. Diazonium cation. And the Aryl ones are the only ones we'll talk about. You can actually form diazonium cations from alkylamines. They tend to be very reactive and very unstable, but the Aryl diazoniums are actually stable. We'll make nitrous acid from the salt form here, from sodium nitrite and HCl, or some other strong acid. Usually HCl is the main one, and so our counter anion here will be chloride, okay? And those salts are just that. They're solid materials that are very stable and well behaved if they're aromatic here. And then we can take different nucleophiles, and we'll go back to the overhead and show those. If you're alive, you can see those different nucleophiles that can be added here to that. And the nucleophile just takes the place of the diazonium, okay? So it opens up a lot more possibilities for different compounds. We won't do the mechanisms here, so no mechs required. We'll just show the reactivity. They actually vary depending on the type of nucleophiles, and some of them are still not too well known. They're kind of controversial. But what we can say about the mechanism is it's not SN2. Okay. Why is that? Because this is aromatic leaving group. And you can see this is potentially a good leaving group, right? And this is just the concept of what's being replaced there. And what you're losing is N2 gas, okay, which is the world's best leaving group, okay? But the mechanisms are varied, and you don't need to know them, okay? But it's definitely not SN2. So that what I'm drawing up there is just conceptually what's going on. Let's look at how these things form. I'll show you a little bit of the mechanism. Well, the structure of this is important to look at. So, what is that? Well, you got benzene, and you got two nitrogens here. And how do we get this plus charge? Well, there's a couple places we could put it. Let's draw a triple bond there. And you see this nitrogen here as we draw it with a triple bond, and the lone pair here, you know, break out your formal charge formula again and go through that. Valence electrons for nitrogen is 5. So 5 minus 4 bonds and no lone pairs, yeah, plus 1 is right there, okay? And what, 3 bonds and then 2 lone pair non-bonded, yeah, that's neutral, okay? We could also draw this, which would be a resonance structure of it. So we'd have aromatic, and then what, lone pair there. And where would be our plus charge? And would be right there on that nitrogen. So either one you can imagine there. And you could actually do resonance into the benzene out here to draw some other things out. But the structure of the aryl diazonium cation is important to keep straight. Let's do a little on the mechanism of forming the aryl diazonium. And I show this, but you know, I've actually never put this on a quiz or a test. I like to show how it works though. Here's nitrous acid. So this is all inorganic stuff. We won't involve any carbon for a while here, sorry. And let's go ahead and protonate that with HCl. So there's our strong acid. And what do we get? We get the hydronium ion on the side here of what will become the nitrosyl cation. And yeah, here it is. So just lose water there. And what do you get? You know, okay. And that's called the nitrosyl cation. That's the thing that's going to do our reaction now. And no, it's the lower oxidation state of the nitronium cation, which is what we did for nitration before. And that was from nitric acid, right? This is nitrous acid, very different material. Anyway, so let's do that. And what? Let's take our aniline. And, you know, before, yeah, if this is NO2 plus, we would nitrate the benzene, okay? With one less oxygen here, it doesn't do that now. This is a nucleophile, and it prefers to add directly to the nitrogen. And there's our nitrogen-nitrogen bond now, okay? So what does that look like? Well, it looks like this. We have 2 hydrogens here, and NO there. We have the plus charge on that. And now what do we got to do? We just got to get rid of water. Okay. And how are we going to do that? Well, we could take off one of these hydrogens. I'll kind of show you the stepwise mechanism, I guess. We're back to neutral there. And what we can then protonate out here, yeah, well, we could have just done that intramolecular there. And so what do we have? NO cation over there now. And then what? Then we can just push these electrons here, to there. We're not involving carbon at all, are we? It's kind of an exercise in pushing electrons. The aromatic, it's the benzene, of course. Now we got a double bond there, and we got an alcohol there. Okay. Not drawing all the lone pairs, but if we do that, what? You need to include the positive charge there on that, right? And then what do we need to do? We need to get, I'll just do it intramolecular to save a little time. Transfer the proton over to oxygen, because what? We need to get rid of water, right? So you can kind of see the logic of this, I think. And where we get the diazo, right? So here we got, showing all the lone pairs and the charge now on oxygen. So how do we get the aryl diazonium? Well, it's right here. There we go. Okay. And yeah, and I'll just draw it as HNO2 plus water. Okay. So the mechanism's not that bad. It's kind of an exercise. And like I said, I never put it on a quiz or test. Why? It's not organic chemistry. It's inorganic stuff, okay? But it does form this very versatile now intermediate here, the aryl diazonium. Let's look at a couple reactions here, and we'll do the synthetic applications on Monday. So we'll have some synthesis problems we'll work using this. But let me show you the reactions it does now. Maybe get this one back up here. So here is our Aryl diazonium down here. And let's show the different reagents that it can react with. These are called Sandmeyer reactions in honor of the guy who developed it. Don't worry about that. But we've got benzene, which came from aniline, right? And we can just say, you know, aniline. And how did we get here? HONO. Like you can just leave it like that, okay? Or you can show the whole thing. You can show sodium nitrite and HCl, okay? Either one of those, you know, to show your Aryl diazonium. But it has to be the regular aniline, okay? It can't be the amide or anything else on that amine. It has to be this aromatic primary amine. You can have other groups on the benzene, okay? So it can be substituted, and we'll see some versatility with that. And then once you have this, let's see if you react it with water and copper oxide, you get the phenol. And we haven't shown you how to make phenols before. So notice that goes from the aniline to the phenol, okay, via the diazonium, okay? In pretty mild conditions. Yeah, you have to have this copper oxide in there, but the water will do this reaction quite efficiently to go from the aryl diazonium in good yield to the phenol. Okay. You can take another copper reagent here, copper chloride, for example, and any copper halide actually will do this. You can do fluorides from tetrafluoroboric acid. Okay, that's a new reagent we haven't seen before, but you see all the fluorides here. And this is a way to finally make aromatic fluorides. We couldn't do electrophilic aromatic substitution directly with F2. Why? Because that's a very dangerous reagent, explosive. Okay. And yeah, we were limited there. But if we use this borofluoride salt, we can actually go to that, no problem. Aromatic fluorides, iodides, and that's just sodium iodide. Okay. And some of these were tempted to say, well, there's our nucleophile. No, here's our leaving group. But again, it's not SN2 chemistry, okay? Some of these mechanisms are pretty well known, and they can be varied. The book just says they're varied, okay? And I could show you a couple of them. The ones with copper are actually the most well-known ones. The copper actually inserts in here. It forms an aryl copper bond initially with the N2 on the copper. The nitrogen then leaves, and then there's what's called a reductive coupling then. Whatever's left on the copper ends up on the aromatic group with the loss of N2. But don't worry about the mechanisms, okay? But just this secondary level of understanding, the reactivity. What reagent goes with the aromatic diazonium? So let's see, a couple more here. Copper cyanide. This is a neat one because it goes to aromatic cyanides. And we know how to do a lot of things with cyanides, right? If we reduce that with dibol and then water, we can go to benzaldehyde. If we react that with LAH, we can go to benzylamine, okay? That's different than aniline, benzylamine with LAH. That carbon in between would be a methylene on that. But the initial product here with copper cyanide is to go to the aromatic cyanide. And then the last one I think we'll show here is using hypophosphorous acid, which is H3PO2, okay? And you can see here, there's actually a phosphorus hydride bond here. You can see how complex that mechanism might be, but this gives the reduced form of the benzene. And you might think, well, that's got to be the world's most worthless reaction, right? It goes back to benzene. Well, that's what we started with to make any of those things, right? Well, no, in the meantime, we could have other things on here, right? And we could use the aniline or a nitro, right? In fact, we can go back here, how we got the nitrogen on there to begin with, right? When we nitrated benzene, or have other stuff on there. And then we do the reduction with tin and HCl, or hydrogen and palladium, right? So you know how to do that step there. And then whatever else we have on here, we can use these as different directing groups. And then those groups will persist onto here. And then where that group was initially, as an aniline or the aryl diazonium, is now reduced. Okay. And let me just, oh, now we're out of time. Here's one to think about. How do you make this compound? 1,3, 5 tribromobenzene, where they're all 3 to each other. They're all mutually meta to each other. Okay. How do you make that? Well, the halogens themselves are deactivating, but they're ortho-para directors. So what do we need to have right here? Well, you might want to think about this hypophosphorus acid at the end here. Okay. That'll whet your appetite a little bit. We'll do a couple more reactions like that, showing you the versatility of the aryl diazoniums and how they can make different things, and show you a couple other applications. But that essentially wraps up everything in 25. But you have till Monday to worry about the homework. Um, and yeah, so no class on Friday. We'll be back on Monday to wrap up and review, okay, and answer questions on anything. But of course, you have Thursday, tomorrow, in the recitations. We can help you out with quiz, what is that, 7 that's on there, okay. So very good, guys. Thank you. We'll see you next time.